Hello, this is Zhi Mao from the Intelligent Imaging Lab at Purdue University. Today I'm going to present our work on simulating imaging through atmospheric turbulence. This is a joint work with Nicholas Schmidt and Professor Stanley Chen. Imaging through atmospheric turbulence is a practical problem for engineers. When images are captured through a long range, the non-uniform refractive index in the atmosphere will cause degradation in image quality. Such degradations may affect many applications, such as navigations, remote sensing, surveillance, and etc. Here are a few examples of turbulence-distorted scenes and reconstruction results. You can see from these examples that the distortion from the turbulence includes spatially varying geometric distortion and blur. Such distortion is resulted from a complicated physical process. To accurately simulate the turbulence effect, one will need to calculate a spatially varying point-spread function for every location in an image. To do the simulation efficiently is a non-trivial task. So why are we interested in the forward model? The first reason is that collecting long-range data for training deep neural network is very difficult. Better synthetic training data will certainly lead to better results. We would also like to generate a large amount of data in an efficient way. We also want to do evaluation. While real data is certainly the best for testing purpose, synthetic data still has its value. It has ground truth for calculating PSNR or SSIM scores. The most popular way to synthesize turbulence data is to artificially heat up the air along the imaging path. Such method may not reflect the true characteristics of long-range turbulence, such as the exoplanetary effect. We would like to have a simulator that is physically verified to synthesize the testing data at all turbulence conditions. This work is built upon our previous work published at the Optical Engineering. In our earlier work, we proposed a collapsed phase screen model. The idea is to directly calculate a phase distortion for every pixel location, which allows us to bypass many tedious calculation of wave propagation. In our earlier work, we used Zernike polynomials to model the phase of the point spread functions. In the optics literature, the phase distortion of the atmosphere can be represented using a weighted combination of the Zernike polynomials. The weights here are called the Zernike coefficients. The structure of the point spread functions are defined through the correlations among all the Zernike coefficients. While our early work has already improved the simulation speed to some extent, it is still not enough. A quick calculation here will tell you that to simulate a proper training dataset for image reconstruction, it will take more than 20 days. There are mainly two bottlenecks that significantly slow down the simulation. Firstly, for every pixel location, you need to calculate a Fourier transform to form the point spread function. Then, you will need to calculate the spatially varying convolution. To speed up the spatially varying convolution, we use a linear expansion model on the point spread functions. By doing so, we can turn the highly spatially varying convolution into several spatially invariant ones and the dot product with a basis coefficient. Here is an illustration of our simulator. Our earlier work has an efficient way to draw the Zernike coefficient, and now we have a way to efficiently do the spatially varying convolution. The only missing piece is how do we link the Zernike coefficients and the basis coefficients. It turns out that the answer is quite simple. We have found out that the transformation between the Zernike and the basis coefficient can be accurately approximated by a tiny 3-layer neural network. Such small model allows for very high level of parallel computation, and hence the simulation can be significantly speed up. Beyond the acceleration, we can now do interpolation in the phase domain. This is a more physically correct way to do interpolation, since naturally the continuity is in the phase distortion of the wave. We've also shown that the impact of the wavelengths on RGB channel is negligible. Here are some results. First, we show the comparison of the tilt and blur against theoretical predictions. Please refer to our paper for the precise definition of the terms. We also show a simulation result with some real data at the same turbulence condition. Here are some visual comparisons, and also the speed comparison. Compared to the golden standard simulator from the Optics Society, we are almost 3 magnitudes faster. Here are some results of training neural networks. The same network trained with our simulator has the least amount of artifacts and close to state-of-the-art performance. Thanks for watching, and don't forget to check out our website for the code and other related works.